invitation.
Okay, so let's just start. It's 8:03. So yeah, it's my great pleasure to have Hakju as a tutorial speaker. This evening in Korea, maybe the early morning in Europe. And Hakju has been one of the leading figures who worked on the traditional problem of program analysis before, but also he was one of the few people who worked on using machine learning techniques for many problems in program analysis as well as symbolic executions. So he has multiple papers that uses machine learning techniques to improve some heuristics used in machine learning program analysis algorithms. So also he worked extensively on symbolic executions, and he's kind of solved or pushed the state of the art of the techniques using many ideas from machine learning. So it's great to have him. And then it's a great kind of opportunity to hear his perspective and experience on how to bring machine learning and program analysis together. So please, Akju, and come and explain to us.
Okay, thank you for introduction. Hello everyone, my name is Hakju at Korea University. And in this tutorial, I'm going to introduce some methodology called data-driven static analysis, which is about combining machine learning and program analysis. So as you know, one of the main difficulties in static analysis is how to achieve scalability and precision at the same time. So typically, a fast static analyzer is imprecise and produces many false alarms. On the other hand, a static analyzer that is precise is often too slow to be used in practice. And this talk is about how to change this situation and how to build a static analyzer that is precise and fast at the same time. And in particular, I'll talk about how to use machine learning techniques to address this problem. So let me concretize the problem with two examples. The first example is flow-sensitive analysis. So suppose we analyze this program with the interval abstract domain. And here variables A and B are initially 0 and C is 1. So the analysis computes an abstract state like this, where variable A has the interval value 0 and B has the same interval and C has the interval 1. And then we analyze the second statement where we update the value of A by C. And at the subsequent statement, we increment the value of C by 1 and update the value of B by A. So the associated abstract stage like this. And at the last statement, we have a program assertion which checks if B is greater than 0 or not. And the goal of the static analysis here is to prove that this assertion always holds during the program execution. And in this case, the analysis can prove this property because as you see, the last abstract state, the value of B is greater than 0. And in this case, the analysis is called flow sensitive. And typically, flow sensitive analysis is quite precise in practice, which means, for example, in this case, this flow sensitive analysis can prove the program assertion at the last statement. But the problem here is that such an analysis is quite costly to separately analyze all the program points like this. So on the other hand, to reduce the analysis cost, we can perform a flow insensitive analysis. And in this approach, we simply compute a single abstract state like this that over-approximates the memory states at all program points. For example, a flow insensitive interval analysis computes this single memory state for the whole program, where program variables A and B are approximated by the interval 0 to infinity and C by 1 to infinity. And in practice, such an analysis is quite cheap, so it scales to large programs. But the problem in this case is that its precision is too too low to be useful. For example, in this case, the analysis cannot prove the assertion. So a practical static analyzer takes an approach between these two extreme cases by selectively applying flow sensitivity only to a subset of program variables. For instance, suppose we apply flow sensitivity only to the variables A and B and analyze variable Z flow insensitively. That is, we keep separate analysis results at each program point for the variables A and B, but for variable C, we compute the single result that is that over approximates all the possible cases in the program. So this way, we can improve the precision of the flow insensitive analysis without increasing the cost too much. But in this case, in this approach, we have to very carefully select the variables. For example, suppose we try to improve the precision of flow insensitive analysis by applying flow sensitivity to variables B and C, then the analysis results looks like this. But in this case, we fail to prove the assertion because the value of B is still imprecise. So the main question here in this approach is how to find a good program abstraction, such as the set of program variables to apply flow sensitivity. And this question turns out to be a very challenging search problem. This is because the search space is intractably large, if not infinite. For example, there are exponentially many different abstractions for flow sensitivity. And even worse, most abstractions in the search space are not effective as they are either too imprecise or too costly. For example, in the previous example, there are 8 different abstractions because we have 3 program variables, but only one non-trivial abstraction succeeds to prove the assertion. So this is a fundamental problem in static analysis, and the goal of data-driven static analysis is to solve the problem using machine learning techniques. Let me describe one more example, context sensitivity. So consider this program, C program. So here we have 4 procedures. Procedure H is an identity function, and it is called twice in procedure F, once with the parameter A at call site C1, and again with an input from the environment at call site C2. And F is called from procedure M and G with different constant values 4 and 8. And M calls G 2 times at call site C5 and C6. And the program also has an assertion right after the call site C1, and it asks whether variable X is larger than 0 or not. And here the assertion always holds because the value of X is always 4 or 8 in the program. But if we analyze this program context insensitively, we cannot prove the assertion. A context insensitive analysis abstracts the program into this call graph, where, for example, 2 different calls to function H at call site C1 and C2 are merged. And similarly, 2 different invocations to function G at call site C5 and C6 are not distinguished during the analysis. So this kind of abstraction is typically cheap in practice, but does not provide precise results. So in this case, for example, we cannot prove that X is greater than 0 at the program point of the assertion because the analysis is insensitive to its calling context. And the unknown value from call site C2 can flow back to call site C1 by passing through the identity function H. And therefore, the value of X at the assertion can be any integer during the analysis. So to fix this problem, we can increase the context sensitivity. And suppose that we use the conventional k-CFA. The k-CFA maintains strings of call sites of lengths up to k. And here k is a global parameter of the analysis, which is fixed during the analysis. And the analysis separates, the k-CFA separates the analysis results for each different call stream of up to length 3. So for example, for the procedure H, the 3-CFA analysis distinguishes these 6 calling contexts and compute the value of n separately for each of these contexts. And this kind of analysis is precise in practice. And in this case, the analysis now can prove the assertion. However, the analysis quickly becomes very expensive as the number of different contexts in a program grows exponentially. So a practical static analyzer applies context sensitivity selectively. So in this case, for example, we can apply 2 CFA only to the function h and 1 CFA to function f, and context insensitivity to other procedures such as G and M. And this kind of analysis produces this call graph. And as you see, this selective k-CFA analysis is much faster than the previous fully context-sensitive one. And at the same time, it is precise enough to prove that the given assertion is true. So again, this is a challenging search problem. And in this case, a program abstraction is a map from functions in the program to integers 0, 1 through k. That is, we would like to assign one of these integers between 0 and k to each function of the program. And again, we would like to use data-driven techniques to tackle this problem. So here is our overall approach. Given a program to analyze, we first run an abstraction heuristic to produce an abstraction of the input program. For example, in flow-sensitive analysis, the heuristic produces a set of program variables that should be analyzed flow-sensitively. And then static analyzer uses this abstraction to perform cost-effective analysis. And traditionally, this abstraction heuristic has been developed manually by human experts, but doing so is definitely non-trivial and time-consuming. And in our approach, the abstraction heuristic is generated automatically from data using machine learning techniques. So the main benefit is, the first benefit is the automation that does not require human effort or expertise. And also, as you will see in this talk, the automatically generated heuristics can outperform manual heuristics crafted by human experts. So over the last few years, we have developed a set of techniques, a set of machine learning techniques for static analysis. And the goal of this talk is to introduce this most successful approach presented at Uppsala 17 and has been used in subsequent work as well. But let me begin with this simpler approach, which is a linear approach presented at Uppsala 15, because this is a quite old technique, but it is useful to illustrate the big picture of the approach. Okay, let me begin with the data-driven static analysis technique with the linear model. So to describe this technique, I'll use this selective flow sensitivity as a running example. And here are some preliminary definitions. So let P be a program to analyze, and A be the space of possible abstractions. So for example, for flow sensitivity, it is a program abstraction for flow sensitivity is a map from variables to binary values, where 0 indicates flow insensitivity and 1 indicates flow sensitivity. Or we can equivalently express this space by the power set of program variables. And let Q be the set of assertions given provided together with the input program. And the goal of static analysis here is to prove these assertions as much as possible. And in our approach, we assume black box access to static analyzer. So the static analyzer is modeled by a function fp, which takes an abstraction of the program and produces two outputs. The first output is a set of assertions or queries that are proved by this abstraction. And the second output is an integer that denotes analysis cost, for example, such as analysis time or memory usage. So, and also let me define two functions, cost and proved. And cost is, I'll assume cost returns the second component of the analysis output, the analysis cost, and the function proved returns the first component of the output, the number of the set of queries assertions proved by this abstraction, by the abstraction. Okay, so let me explain our approach. So in general, a machine learning method consists of 3 steps, and we also follow this standard practice. So first, in the first step, we have to define a parameterized model. In our case, a parameterized heuristic, denoted by h-pi. The input to this heuristic is a program, and the output is a set of programs to analyze flow sensitively. And here, pi is the learnable parameter of this model, and the effectiveness of this heuristic is entirely controlled by this parameter. And second, the learning object, the second step of machine learning is to define the learning objective as an optimization problem. And in our case, the optimization problem is to find a parameter pi that maximizes some analysis performance. And the last step is to solve this optimization problem by a learning algorithm. So let me explain these 3 steps in more detail. First, parameterized heuristics. So recall that the heuristic can the heuristic takes a program and returns a set of variables in it. So to do so, our parameterized heuristic takes 3 steps. First, we represent program variables as feature vectors. Second, we compute the score of each variable. And finally, we choose the top k variables with the highest scores. So let me go through these steps in more detail. So first, this page, in this page, let me explain features. So to enable machine learning, we need some features. So we assume a set of features is given. So in this case, a feature is a predicate on program variables. For example, we can use simple syntactic features such as is it local variables, or is it global variable, or is a variable passed to some function as argument, and so on. And by assuming these features, for example, 5 features, we can transform variables to feature vectors. And so, for example, assume variables x, y, and z have these feature vectors. And the second step of the parameterized heuristic is scoring. We define the parameter pi to be a vector of real numbers between -1 and 1. For example, assume pi is this vector, 0.9, 0.5, -0.6, and so on. Then we can compute the score of variables by linear combination of feature vectors and the parameter vector. So the score of x in this case is 0.3, y 0.6, and g 0.1. The last step of the heuristic is to choose top k% of variables based on their scores. For example, when you select 66%, we choose the variables x and y. So in practice, we choose 10% of program variables because empirically, this number was good for striking the balance between precision and scalability. So let's move on to the next step of machine learning. The second step. So the goal of learning is to find a good parameter vector pi using a data set of programs. So we assume a collection of programs is given, and this goal, learning objective, can be formulated by this optimization problem. That is, we would like to find a parameter vector pi that maximizes the analysis precision over the training data. Next, we have to develop a learning algorithm to solve this optimization problem. But in this case, because we only assume black box access to static analyzer, it is difficult to develop some good algorithms, bright algorithms. So a simple method is just using random sampling. We randomly sample the parameter vector and evaluate the objective function with the sample parameter, and we repeat this process until time's out, and then return the best parameter found so far. So this is a very simple algorithm, and if you are interested to improve the efficiency of this learning algorithm, you can see our paper that uses Bayesian optimization to optimize this learning algorithm. But although simple, this algorithm was quite effective when you implemented it in Sparrow, an interval domain static analyzer for C programs. The precision of this data-driven flow sensitivity was about 70% of the full precision, but it increased the analysis time of flow insensitive analysis by 2 times. But full flow sensitivity increased the analysis cost by 18 times. However, However, it was not effective enough in practice. For example, when you applied it to context-sensitive point analysis for Java, its performance was like this. So was like this. So this is the for 2CFA. This was the full precision, the most precise abstraction produced about 1,200 alarms with 2,500 seconds, and the context insensitive analysis was much faster, but produced significantly more alarms. And our analysis improved the precision of the context insensitive analysis quite significantly, but it was not more effective than the manual heuristics developed by the analysis expert. But this is not a fundamental limitation of the data-driven static analysis, and we can improve its performance using the next version of this simple algorithm. So let me explain a data-driven static analysis with disjunctive models. Sorry. Okay. So let me first identify the key limitation of the previous approach. So the previous approach used a kind of linear heuristic. So it was not possible to express some complex program properties, in particular disjunctive ones. For example, suppose there are 4 program variables, x, y, z, and w, And suppose x has two features, a1 and a2, and y a1, g a2, and w does not have any meaningful features. Then the previous method, with the previous method, we cannot select this set x and w, because to do so we need some disjunctions. So this was the key limitation, and we would like to fix this problem. And in this case, I will use context sensitivity as a running example, because this is more challenging problem. And here is the learning algorithm overview. So our algorithm takes 3 inputs. First input is a static analyzer, and the second one is training data. And in our case, training data is just a set of programs, and the final input is a set of atomic features. For example, let me assume we have 25 features about procedures. For example, a feature may describe whether the procedure has an invocation statement in its body, and so on. So given these 3 inputs, our learning algorithm produces this kind of abstraction heuristic. So basically, it produces 2 Boolean formulas, F1 and F2. And F2 describes the set of procedures, set of functions that should be analyzed with 2 context sensitivity. So this means that we have to apply 2 context sensitivity to procedures that have the feature number 1, and it does not have the 3rd feature, does not have 6th feature, have the feature 8, and so on. And F1 means the set of procedures that should be analyzed with 1 context sensitivity. So in this case, for example, those procedures should have the first feature, not 3rd feature, not 4th feature, and so on. And the important thing here is that we express these properties with these disjunctions. So again, preliminary definitions. We assume a program to analyze is given. And here, K denotes the degree of abstraction. For example, for 2 CFA, K is 2. And for flow sensitive analysis, K is 1. And A is the set of possible abstractions for the program P. So A is defined to be a map for context sensitivity. A is a map from functions in the program to integers between 0 and k. And again, Q is the set of queries in the program. So the first input to our algorithm is a static analyzer. And again, we assume the function fp. The static analyzer is modeled by black box function fp, which takes an abstraction and returns two outputs. The first is the set of proved queries, and second output is the number, integer, denoting the analysis cost. And we assume cost and proved. And the second input is the training data, a collection of programs, P1, P2 through PM. And the third input is a set of predefined features, and we assume n features. And in this case, for flow sensitivity, a feature is a predicate on functions. So it is a map from functions to true or false. And a feature denotes a set of functions. Its meaning is the set of function m, such that m feature ai denotes a function m if m is implied by the feature ai. And the output of this algorithm is abstraction heuristic. And in this case, the abstraction heuristic takes a program and produces a map from functions to numbers 0, 1 through k. So intuitively, the abstraction assigns one of these integers between 0 and k to each function of the program. And given this abstraction heuristic, we can use it to analyze new program P. So by first applying the heuristic to the input program P, so H of P produces an abstraction, and use that abstraction to analyze the program using the static analyzer FP. Again, we follow the standard 3 phases of the machine learning process. So first we define a parameterized heuristic, and in this case, it takes a program and produces a set of functions, and define optimization problem, and third, learning algorithm. So the first step, parameterized heuristics. So in this approach, the heuristic h pi has k Boolean formulas as learnable parameters. So the pi, unlike the previous approach where pi was a vector of real numbers, in this case, pi is a vector of k Boolean formulas, where k is the degree of the abstraction space. And each formula fi is defined over the atomic features. So f is either true, false, atomic feature, or negation of some formula, or conjunction and disjunction. And intuitively, a formula denotes a set of functions. For example, true, the formula true denotes all the functions in the program, and false, empty set, f1 and f2 corresponds to intersection, and so on. Sorry. Okay, so the parameterized heuristics. So let me define the heuristics. So recall the type of the heuristic. It takes a program and returns a map from functions to integers between 0 and k. And suppose we are given a parameter vector of k Boolean formulas. Then our heuristic produces this abstraction. Abstraction is a function, is a map from here m is a function in the program, and I is one of the integers between 0 and k. And we assign I to function m if m is implied by the formula fi. So intuitively, we assign okay, let me explain with an example, with the running example. So in this example, let's assume there are 5 features, A1, A2 through A5. And suppose procedure H has 3 features, A1, A3, and A5. And procedure F has A3 and A5, G, A1, 2, 3, and M, A2, 3, and 4. And consider a heuristic H or H with F1 and F2. So now we are considering 2 CFA. That's why we have only 2 formulas, F1 and F2. And assume F1 is this formula, negation of A4 and A5. And F2 is a disjunction of A1 and A5, and A2 and negation of A3. So in this case, the formula F1, the meaning of this formula F1 is the set of procedures F and H, because F and H satisfies this formula. And F2, the meaning of F2 is H, because the procedure H has only the procedure H satisfies the Boolean formula F2. So with these 2 formulas F1 and F2, our heuristic produces the abstraction where H maps to 2 f to 1 and other procedures to the degree 0. Because, for example, note that h is implied by both f1 and f2. In this case, we assign the greater degree 2. And f is implied by only by f1, so it is assigned 1. And other procedures, G and M, are not implied by any of the formulas here. And in this case, we assign the least degree. So our heuristic works like this. So the second step is to define the optimization problem. And in this case, we define the optimization problem as a minimization problem, such that we would like to find a parameter vector pi that minimizes the cost of the static analyzer of the training programs. But we have to make sure some precision constraint, because without any precision constraint, finding the solution that minimizes the cost is trivial. We can simply find the least precise abstraction. So our optimization problem ensures or usually takes a user provided precision constraint, for example, such as we would like to maintain 90% precision of 2 CFA. And this kind of precision constraint can be expressed like this. Here, the denominator denotes the number of assertions proved by the most precise abstraction, 2 CFA here. And the numerator represents the number of assertions proved by the current abstraction. And here on the right hand side, 0.9 denotes the 90% precision. So like this, we can define the optimization problem. And finally, we have to develop some learning algorithm to find a good parameter of the heuristic. And in this case, we have developed a greedy algorithm based on iterative refinement. And let me skip the detail of this algorithm. And if you're interested, you can see, you can consult our paper. So let me briefly check the effectiveness of this approach. So now, our data-driven approach can outperform the hand-tuned heuristics. So for example, for context-sensitive pointer analysis for Java, recall that the linear approach was less effective than the manual heuristic. But with the new disjunctive algorithm, we could achieve very ideal analysis, which is as precise as the most precise abstraction, and also its cost was comparable to that of context insensitive one. Okay, let me summarize. So in this tutorial, I introduced a data-driven static analysis framework, which can be used to generate analysis heuristics automatically from data. And you can see more recent results in my web page. For example, in this talk, I assumed the features given by the users of this framework. But in some cases, we can automatically generate the features as well. And also, although I didn't talk some details, this framework is applicable to monotone static analysis. But there are many instances of non-monotone analysis, for example, analysis with widening. And in this case, we can apply another machine learning algorithm. And also, we can apply this idea beyond the static analysis. to, for example, symbolic execution or concurrent testing. Okay, thank you very much. And if you have any questions, please let me know.
Okay, so thank you very much, Hak-Chu. And if you have any questions, then you can post it in the chat box or in the Q&A. Or if you raise your hand, then I can invite, maybe you can invite you so that you can speak to Hak-Chu directly. So while we are waiting for some questions, I have a few questions that I want to ask. So the first question is, I think when you try this static analysis, you use some training set, which is a collection of programs, and you train these heuristics, and then you apply the learned heuristics to programs which is outside of the training set, so which may be much larger programs and so on. So typically such a thing is in statistics and machine learning, it's called extrapolations. So it's really reasoning about something which is outside of the training set. And that problem, the doing good extrapolation in the standard statistical problem is very difficult. But on the other hand, in your case, looks like some of your experiment shows that you can learn nice heuristics from small programs, and that heuristics can be applied effectively for very large programs. And can you kind of tell us why, what aspects of a programs makes these extrapolations possible, or maybe, yeah. So can you make some comments about this?
Yes, that's a great question. So for example, in this case, for when we train the context sensitivity heuristic for point analysis for Java, we only used 4 small programs and only used 4 small programs to produce a general heuristic and used it to analyze other multiple programs. But according to our experience, this worked well. And I think because even though I said we trained on a small program, those small programs are not very small in practice. They are realistic enough according to our experience. So that's the one reason. And the second reason would be for Java applications, they may share some shared libraries, and those libraries can be commonly used by different applications. Yeah, maybe that would be second reason. So a kind of, you can feel a kind of cheating here, but that's the common properties of Java applications. Many different Java applications are actually similar in terms of the libraries they use.
I see. Okay, so thank you very much. So there is actually one question. Would you click the one, how do you choose features? Well, okay, that one is also better. Yes.
How do you choose features? Yeah, that's a very good question. So actually, this is an art. So currently, this is an art. So we have to, and this is where the analysis experts kicks in. So those features should be designed by domain experts, the analysis experts. So this is one limitation of the techniques that I talked about today. But in some cases, we can design a learning algorithm that does not depend on those manual features. For example, in our recent Uppsala 20 papers, instead of designing manual features that are specific to each analysis instance, we instead designed a generic feature language, and so that feature language can be reused for different analysis instances. But still in this case, we have to design the feature language. The analysis design, the expert should design the feature language, but it can reduce the burden significantly in that case.
I see. So can you tell us a little bit more about your experience? Because you use machine learning for static analysis as well as symbolic executions. For these different type of applications, can you give us some examples which illustrate, I mean, the choice of different features matters very much for these different applications. So, for instance, if I design features for like a context sensitivity static analysis, and then use exactly the same set of features for symbolic executions, I expect it breaks, but can you tell us about why it's going to break? And then maybe what kind of extra features I have to add in some high level?
Yes, but yes, that's a great question, but a very difficult question to answer because first of all, for context sensitive analysis, the features we used were very primitive. For example, most of the features describe lexical properties of the method. For example, the type of the return type or argument type, and whether the method body includes some type of assignment or not. So very primitive features that does not require much ingenuity. But in other applications, for example, in symbolic execution, we had to come up with more sophisticated features that can be only designed by experts who well knows the symbolic execution details. But yeah, frankly, I don't know why, but that was our experience for but it is quite difficult to say general lessons about features currently.
There is also questions. I mean, I think what do you mean? Yeah, data driven.
Yes, data driven means the use of machine learning and data.
Good. And then there's also one more. So you start from the trivial Boolean formula.
Yes, actually, I didn't talk about the details of the learning algorithm, but the rough idea is that we begin with the trivial formula whose semantics is true. And then we iteratively refine the formula so that it means smaller set of procedures. That is the very rough sketch of the algorithm. Yes, your understanding is correct.
So let me add kind of to the follow-up for that questions. So I mean, the one difficulties of using your techniques for static analysis or symbolic execution, or maybe other kind of programming language related activities, is to design features. But the other difficulty comes from solving optimization problem, because features and so on, they let us phrase this abstraction finding or heuristic finding as a search problem, but then we need to do search. But like this particular examples, I mean, looks like it's not a very easy search problems. How do you come up with a effective way for solving this type of search problem? And also, is this difficult search problems in your experience arises often in your applications of machine learning in PL?
Yes, one of the main difficulties is how to come up with efficient machine learning algorithm. And yes, I didn't talk about the details, but one thing we exploited for efficiency was the monotonicity of the program analysis. So when the analysis is monotone, we can significantly reduce the search space without losing a chance of finding good solution. And that was in the details in our paper. But so first we reduce the huge search space into much smaller one, but still the reduced space is still huge, but much smaller than the original problem. So we can start from better search space, and then we have designed the second reason. The second reason for effectiveness was we have designed the so-called greedy algorithm, but this algorithm has pros and cons. The pros is that we can accelerate the search process, but the cons is that we can lose some opportunity to find a best solution. So maybe the most important one is the reduction of the search space.
I see. So there's a new question. Just curious. Would you again? Would you? Yes. Thank you.
Precision means the number of alarms produced by static analyzer. So we basically assume that the alarms are false alarms because there are much more false alarms than true alarms. So we just count the number of alarms produced by the analyzers.
What about cost?
Cost is analysis time.
Okay. And is this the same thing that you used for symbolic execution as well?
For symbolic execution, we used coverage information.
I see.
Yeah, not because it does not have false alarms, and it rarely produces real alarms. So it is difficult to use the number of found errors or number of alarms as the precision metric.
So in your presentation, in the first example, you put a bound on the cost by setting k to be equal to like 10%, and then you said the optimization is over the precision. But for your second example, you said you put a bound on the precisions, and then you optimize for the cost. So is there any reasons why you took this different approach for these? For different this learning objective for these two approaches?
That is because in the second approach, it was not natural to put a bound on the predetermined bound on the precision or cost. So that was the reason, but no particular reason for that. Yeah.
So any other questions from the audience? I can't. Oh, there's one more. So you have a question? Yes.
Actually, I'm not a machine learning expert. Actually, in our work, we use the very simple approaches, machine learning approaches, and adapted those approaches to tailored those approaches to static analysis. And in fact, I also would like to find some way to apply the state-of-the-art machine learning algorithms to static analysis or PR techniques. But for example, neural networks. But we tried, but it was also not trivial to apply neural networks to, for example, static analysis because of other issues such as representation and the algorithm, the neural network algorithm themselves are black box and so on. So to answer the question, maybe according to my experience, applying simple algorithm was also effective than the manually tuned heuristics. So it would be not very difficult to apply to start these data-driven techniques to apply them to PR techniques.
So we have perhaps one or two more questions. While waiting it, maybe can I ask one more? So you have been working on these directions quite a while in the software engineering problems as well as PL problems. What do you think would be the open problem? What needs to be done next? So you solved many, but what are the remaining problems in this domain?
I think one. There are many directions. I think one would be to use more involved techniques developed in the machine learning community to bring those techniques into this problem. But yeah, that would be interesting future work. And also quite different direction would be to apply the machine learning techniques developed by our techniques, to apply those techniques into the tasks in the machine learning community. For example, recently, in our UPSLA 20 paper, we have designed a feature language and learning algorithm based on some domain-specific language, and we found that kind of algorithm is applicable to general machine learning, like learning on graph structured data, for example. So,
yeah, just adding some comments. I have one of my colleagues working on database. He told me that actually in the database community, they design a language for specifying features. I don't know what else they've done, but that is also one of the, active research topics that people are working on in that domain. Okay, if we don't have any questions, then maybe we can finish. And so let's thank the speaker, and thank you very much for giving very nice talk.
Thank you very much. Thank you.
Thank you.
Thank you.
Yeah, thank you.
Yeah, you too.
Yeah, it's very good.
Yeah.
Actually, just left.
Well.
Okay. Yes. So I will be back. In the keynotes, maybe which will happen like a few hours later.
Great.
Okay.
Is it
So,
too late for you?
yeah, it's a bit late, but I'm in my office now. So if I go back to home, that should be about time to watch another video.
Okay, that's great. So I'm gonna end this session.
Yes.
Okay.
Okay.
Thank you.
So thank you very much, and thank you all for attending it.